here in the multivalent field, the challenges are quite many and they are large, so it's important that we discuss them, collaborate, and work on them together. Here's just a brief outline of my talk. I'll try to tell you just briefly some info about multivalent group at NIC. Then I'll introduce motivation for the multivalent metal organic battery research. I'll spend then most of the time on Anthraquinone-based polymers as cathodes for multivalent batteries. And then I'll speak a bit about mechanism investigation, where I'll present two methods, so Operando ATR infrared and ex situ X-ray Raman spectroscopy. So I come from the National Institute of Chemistry in Slovenia, which is located here in the border of the Central Europe and the Balkans, just below Austria. You probably pass it when you go to Croatia, to the seaside in the summer. And we are quite famous, not just about batteries, but also sports. And today we have a game. So we'll see if Germany will be better or an air of Nowitzki with Slovenia will be better. So, but now let's go back to the battery research. So we try to do multivalent battery research in several fields. So we started with magnesium, but now we also expanded it with aluminum, calcium, and zinc. And there will be two posters from my colleagues, Clement Pirnat and Svit. We try to combine these multivalent metal batteries with organic cathode materials. So this was already mentioned a bit today, and I'll talk a bit more. Then we try also to do salt synthesis, which is extremely important, and there's also a poster by Tjaša Pavčnik. And we try to keep our solvents as pure as possible, because we know this is extremely important. We also did some work on sulfur, with magnesium sulfur and calcium sulfur, and we try to do with characterization to rely on infrared, impedance spectroscopy, where there'll be a talk by Olivera Lujanin tomorrow, electron microscopy, and XPS, which we got recently. The full battery group, which is headed by Professor Dr. Robert Dominko, is around 30 people, but around there we are like 6 to 7 people working on multivalent. So now let's go to the multivalent metal organic batteries. Actually, why do we need new battery technologies? So if we take a look at the projected needs in batteries up to 250, we see here it's the number of devices, and here it's the energy storage demand. And while the number of devices in portable electronics is huge, the energy storage demand is not that large. But then when we go to automotive applications and energy storage, this demand goes up quite a lot. And if we put these numbers into perspective, we see that Tesla Panasonic Gigafactory in Nevada produced 37 gigawatt hours in 2020. So we can compare this with this number, we see this is really small. And today, I think there are like 100 gigafactories coming up all around the world. And this means huge demand for resources, and many of these resources currently used in lithium-ion batteries are becoming critical. So this is documented by European Union, so listing critical raw materials in lithium-ion batteries, and we can see basically almost all of them are listed as critical. So cobalt, lithium, graphite, silicon, titanium, niobium, and recently, in February of 2022, nickel was listed as critical raw material by United States Geological Survey. So most likely also Europe will follow. So it's important that we develop new technologies that basically will alleviate this burden from lithium-ion batteries and make this demand for raw materials smaller. So if you take a look what we have on offer on alternative metal anodes, there's quite a lot, and I won't spend a lot of time speaking about the benefits of gravimetric and high volumetric capacity, but there's a cost that we pay basically with lower redox potential. So when we go from calcium, we lose just a little, but then moving from magnesium to aluminum, we basically, each time we lose 0.7 volts. So basically, the voltages of the cells that we can assemble will be considerably lower. Another important thing to consider is that while the multivalents are less prone to dendrite formation, this does not mean uniform deposition. So if you read in many articles that magnesium deposition is non-dendritic, don't assume uniform deposition. You should always check how it is going and in each specific electrochemistry conditions and in specific electrolytes. There are also a lot of challenges in application, and mainly these are connected with the fact that when we have passive layers in multivalent electrolytes, they typically do not conduct ions. And this formation of passive layers is strongly connected with their redox potential. Because we know that calcium, it's really close to the lithium. It basically always, it decomposes the solvent and salts and forms passive layer. While in case with magnesium and aluminum, with this redox potential is slightly higher, when we have suitable solvents and salts, we do not form passive layer. And if we put these electrolytes, we can put them like in family generation, and we can consider magnesium like grandpa of the family, because magnesium plating and stripping, it was demonstrated already 100 years ago. Then we have aluminum, which was demonstrated in 1970s, and calcium, it's a new kid in town, because this plating and stripping, it was demonstrated only recently, less than 10 years ago. Due to this fact, there are relatively small amount of electrolytes available, but the largest amount of electrolytes available are in a magnesium. We have basically quite wide choice of electrolytes. We have Grignard-based, we have magnesium chloride-based, and very recently also chloride-free electrolytes. These chloride-free were pioneered by Toyota and also here group at KIT. With aluminiums, we have very few electrolytes, which enable reversible plating and stripping, and all of them are aluminum chloride-based, so it means we have corrosion issues. And with calcium plating and stripping, we have seen today that it was realized only recently in 2019 at room temperature. On the cathode sides, it's quite difficult to insert and desolvate ions. We have issues with solid state diffusion and poor conductivity, and also materials are quite often prone to conversion instead of ion insertion reactions. This leads us to the fact that basically the standard magnesium cathode material is still 2 decades old, Chevrel phase, which was demonstrated by Auerbach in 2000. And unfortunately, we still don't have enough cathodes that would work really well. And this one, while it's well reversible, it has relatively limited capacity and also only moderate voltage. So what can we do? We can move through going from inorganic to organic materials. So in inorganic materials, we typically utilize oxidation and reduction of transition metal, like here in case of lithium iron phosphate. But in organic materials, we basically have oxidation and reduction of redox group. And we can divide these materials basically into groups. We have N-type materials, which accept electrons and become negatively charged, and then they need positively charged cation. And then we have P-type materials, which give away basically electrons and become positively charged and require an anion. This already gives us quite important message that basically, if you want to have operation in low electrolyte condition and cation storage, we need N-type materials, and we want to have anion storage, we need to have P-type materials. So basically, if you want to work with multivalent metals, we need N-type materials. So if you take a look at the N-type compounds that are there, we basically have quite a few of classes, and most common are conjugated carbonyls. Then we have organodisulfides, conjugated azo groups, and conjugated nitriles. But among those two, basically conjugated carbonyls and conjugated azo groups are the most interesting for high energy density application. This is because we can incorporate multiple groups in relatively small framework, and we achieve high capacity. Unfortunately, these typical voltages of organic materials, they are below the conventional inorganic cathodes. So it means that the voltages will be typically always below 3 volts, which is actually in multivalent battery research is kind of a good thing because we don't have really high voltage electrolytes. And like I said before, for having high energy density and operation in linear electrolyte condition, we need to really utilize fully dissociated cations. So it means that we should not have ion pair storage. We should put in just calcium 2+, magnesium 2+, or aluminum 3+. And if we take a look at organic active materials, they have several advantages. Like in a fairy tale, we have high energy, high power, at least from gravimetric point of view. They're relatively abundant and can have low environmental footprint. And in theory, if we have proper materials, they can be even biodegradable. They're also quite versatile, and we have here example basically of operation of various cations. And with some redox tuning, we can also adjust their potentials and capacities. Of course, everything is not a fairy tale, or in every fairy tale there's a dragon. And we have disadvantages, which are low gravimetric density, because basically always the density is below 2 grams per square centimeter, which per cube centimeter, which leads to low volumetric capacity. Additionally, there is low electronic conductivity, which means that we need to add relatively higher amounts of carbon black. And simple organic compounds, they often suffer from dissolution, so it leads to poor cycle life. So we have to somehow mitigate this. And if we speak about lithium organic batteries, we often need to pair them with metal anode, which leads to lithium dendrites. And we have quite some inorganic battery field. There are some quite basically approaches how to address the dissolution of organic materials, and we can graft them onto solid support, like here, which is like putting them on silica. We can prepare polymers and increase their molecular weight and make them less soluble, or use ion selective separator. So each of these approaches comes at the cost of decreasing their gravimetric energy density. So we found, and also the literature kind of agrees, that basically the best compromise is somehow to prepare polymers, but we have to keep in mind that this linker unit should be small. So if this linker unit is large, we basically decrease their capacity too much. Now let's move to the actual research, and I'll spend just 2 slides on the methodology because I think it's quite important to get a feeling how do we do research and what approaches do we use. So we typically, all the organic materials that we synthesize, we test them in lithium metal setup. This allows us quite wide choice of solvents and salts, and allows us to optimize their capacity, and also later we can get a useful benchmark, because typically we believe that if you cannot achieve a capacity in lithium, you will not also achieve it in a magnesium. And also if you have higher capacities, let's say in magnesium, most likely you are having side reactions or different phenomena ongoing. There is really important to evaluate multivalent metal plating and stripping beforehand, especially if you're doing cycling in half cells. This gives you then information about Coulombic efficiency and overpotentials that you can expect. And also because organics often contain carbonyls or sulfur groups, you need non-nucleophilic electrolytes so that you prevent side reactions. Then we typically do our testing in 2 electrode setup in either swedge lock or pouch cells. And one thing which we find also quite important, because in organic field there are quite a lot of carbon black is used, to cycle plain electrodes. So electrodes composed of only binder and carbon black to see their capacitance contribution and to probe for side reactions. Because often when you see electrolyte papers, they are done with low surface area electrodes, metal like platinum, aluminum, but then when you employ high surface area carbon electrode, you have a lot more side reactions. So this is one of the ways to really estimate how much of side reactions you will have. And now let's move on Anthraquinone-based polymers as cathode for multivalent batteries. So anthraquinone is this organic group, which is quite known from organic chemistry. From many years ago, it was first used as basically a framework for making different colorants. And it has relatively moderate voltage potential, around 2.2 volts of lithium, and capacity which is not extremely high, so 257 milliamps per gram. Like we said, this is quite soluble, so it's good to prepare polymers. And if we utilize this cross-coupling polymerization with nickel cyclooctadiene, we can basically get this polymer. We basically do not lose any capacity because we connect the groups together, and we basically slightly increase it because we remove this to hydrogen, and the redox potential stays roughly the same. And then we apply it to the electrochemical testing, and like I said before, we benchmark it first with lithium, and then basically we tested 2 magnesium chloride containing electrolytes. So magnesium TFSI with magnesium chloride, and magnesium chloride with aluminum chloride. So these were 2 of, let's say, most popular electrolytes in the past years. And we can see that there is quite significant difference. So the theoretical capacity should be somewhere here, but already in lithium we don't reach it. So we are reaching only 220 milliamps per gram, and then we have also, although this is a polymer, there is a fade of capacity. And then in magnesium, there is a big difference between magnesium TFSI and aluminum chloride-based electrolyte. We can see that this one has much higher maximum capacity and also better capacity retention. We can also cycle it for quite some time, so we can achieve 500 cycles, which is quite good, and we still have 100 milliamp hours per gram of capacity, which is, let's say, not perfect, but quite good for magnesium. But then the question comes, what do we actually store inside? Are we storing magnesium 2+, or are we storing something else? So to investigate this with this SEM-EDS ex situ, so basically to probe elemental composition of discharge electrode, And what is interesting here, that you can see that basically when we have discharge electrode, we have both magnesium and chloride inside. And the ratio between them is around 2.5. So this means that basically we are storing both at the same time. We are storing magnesium 2+ and magnesium chloride plus. And the ratio between them, it's around 60% of magnesium 2+ with 40% of magnesium chloride plus. So this is somehow, it's not really good because basically we are utilizing the salt. So it means that if we would want to build really high energy density battery, we would need to have considerable amount of electrolyte there. Here we also investigated something else, and also effect of the electrolyte on the redox potential. And actually, when we compare the redox potential of magnesium TFSI and aluminum chloride-based electrolyte, we can see that here it's around 1.55 volts, and here it's around 1.85 volts. And it means that most likely there is some kind of electrolyte and active material interplay, which somehow upshifts the potential of electroactive group. We investigated this by adding aluminum chloride to magnesium TFSI. And what could we observe that actually also in this case, the redox potential upshifted. So it means that we have somehow interplay between our anthraquinone group and aluminum chloride, which moves our potential up for approximately 0.3 volts. So now we decided with new electrolytes to really move on with chloride-free electrolytes because also the cell assembly is much easier. And this is magnesium fluorinated pinacolato borate electrolyte, which is quite similar to magnesium BHF-IP. It only has slightly improved performance in terms of overpotential and efficiency. We use similar cathodes, only in this case it was polyanthraquinone sulfide, so we do not directly cross-couple, but we have these sulfur linker units. And we can see that basically we have quite good rate capability performance. We can operate up to 20 C, although at 20 C there is mostly capacitance contribution left, so there is not much redox capacity left. But we have relatively limited long-term performance because basically we see that our capacity, it fades from approximately 180 milliamps per gram to 60 milliamps per gram in around 100 cycles. But now what we are actually mostly interested in, what is the redox mechanism? Does it stay the same or it changes? So we did XC to infrared insight into cathode electrochemical mechanism. And these carbonyl groups here, they have a specific carbonyl double peak here at 1670 and 1650. And we can basically see that during discharge, it goes down and then it goes up during charge back. There is also a new peak forming at 1378 or 79, which is consistent with this enolate group here. But what we are a bit surprised, basically, that we saw here some additional bands which are not belonging to the electroactive group, but they are belonging to the anion. Because this electrolyte, in theory, should be weakly coordinating anion, so it means the interaction should be weaker, so we should have better let's say, separation between cations and anions. Again, we utilized SEM-EDS for monitoring of the magnesium species. And we saw that basically, yeah, we have a lot of magnesium inside, but there is also fluorine increasing during discharge. So it means that still there is a contribution of anion there. It is decreased because the ratio is 4:1, and before we had 60:40, but it's still there. So it means even with this new class of electrolytes, which are weakly coordinating anions, the contribution of ion pairs is still there. And now let's move briefly to the aluminum battery system. So like I said before, the stripping and plating was demonstrated in the 70s. We basically rely on this electrolyte, which is eutectic mixture of ionic liquid, ethyl-methylimidazoleum chloride with aluminum chloride. And it has a limitation of being highly corrosive and low oxidative stability up to 2 volts. So we use pouch cell with molybdenum current collectors. This aluminum battery work, it was demonstrated quite some time ago in 2015 with this quite impactful publication where they use graphite cathode, but actually there they are not storing aluminum cations, they are storing aluminum tetrachloride anions inside. So this has really important implication because actually aluminum metal anode is not the anode in this system. The anolyte is basically aluminum chloride, which is here inside the electrolyte, and basically we need quite a lot of it to form these ions, and this limits our anode capacity to only 50 milliamps per gram. So this is a huge decrease from almost 3,000 milliamps per gram of aluminum metal anode to only 50 milliamps per gram. So now we wanted to see what does happen when we put organic cathodes, and again we start with this anthraquinone, and we saw that basically it performs quite well. We have good reversibility, a bit interesting behavior because we have some activation of capacity, and also at start we have two plateaus, so one at 0.8 volt and one at 1.1 volt. But then the capacity slowly fades. And we saw that basically this 0.8 volt is what we would expect because the difference between lithium and aluminum is around 1.4 volt, and anthraquinone has 2.2 volts potential. But most likely, due to the fact that we have aluminum chloride in this system, we have basically upshift of the potential of an anthraquinone group. We confirmed this also electrochemical mechanism by Operando infrared, where we can see quite nicely basically that during discharge, we have decrease of intensity for this carbonyl band, and then this is going up during discharge. So it means that performance is quite well reversible. So we wanted to improve the long-term capacity retention, so decided to prepare polymers. And again, we relied on PAQS polymer with CNTs. And we could see that basically we get much better performance because we added CNTs. Also, the accessibility of electroactive groups is much better. And we obtain already in the first cycles 190 milliamps per gram, and then we have quite fast fade, but quite stable performance. And after 50 cycles, we get still more than 120 milliamps per gram of capacity. Only what was a bit troubling is the fact that basically we have a degradation of electrochemical plateau, because we can see that basically this plateau is getting less evident from cycle to cycle. The rate capability was also quite good. At 10C, we're still obtaining more than 120 milliamps per gram. And it was also interesting for us that actually it was better performance than in magnesium system. Then we moved on the mechanism investigation. And we did it first with XPS. So basically we saw here in oxygen that basically we have a decrease of this carbonyl peak during discharge and going back. But during the discharge, we have increase of aluminum species and also chloride species. This initial chloride species is from the monomer unit, which was synthesized from chloride, but then we have additional chloride coming in. So this means that we still have some chloroaluminate species there, although this contribution then decreases in discharge. We did again SEM-EDS, and this pointed to the ratio between the chloride active and aluminum to around 1. So it means that probably we have aluminum chloride 2+ as dominating species in our discharge cathode. This means that our maximum anode capacity increases quite a lot from this 50 milliamps per gram to almost 344 milliamps per gram, but actually it's still far from the theoretical capacity of aluminum metal anode, which is almost 3,000. So we applied the same polymer also to calcium organic battery with this electrolyte, which is developed here. And we saw, like it was shown before, that we have rapid capacity fade. So basically, after 6 cycles, cell is completely dead, and we have no more cycling. To somehow explain this, we decided to apply 3 electrode cell to separate the contributions of the anode and the cathode. And this was actually quite nice because we saw that basically there is no significant increase in the polarization in the performance of the cathode. But on the calcium metal anode, there is basically this bump, which is originating here. It's at the start of calcium stripping. So most likely this is contributed to decomposition of the electrolyte on the calcium metal electrolyte interface. And according to the literature, it can be most likely attributed to calcium fluoride forming there. So it means that basically the calcium electrolytes are still far from perfect, although they enables us to do cycling of our batteries for quite some cycles with good performance. Situ-ER was quite similar to the magnesium case. Again, we saw a decrease of the carbonyl intensity and new peak here. And again, there were contributions of the anion, which was then also converted to SEM-EDS. And when we take a look at this fluorine, which is active here, we could see that basically there's a ratio between calcium 2+ and calcium BHF-IP between 3 to to 2. So basically, still there is quite significant contribution of ion pairing here. I would have to state also something here that this SEM-EDS, this is not super quantitative estimation. This is more qualitative. So don't take these numbers with all the precision that you see here. So it's qualitative assessment. So just to shortly recap this part is like that we have organic electrodes and they clearly offer a perspective for development of multivalent batteries. We have quite a drop in capacity utilization when we move from lithium to multivalence. And anthraquinone type of compounds, they are quite good models, and they offer reversible performance in all magnesium, calcium, and aluminum. Of course, there is much more work to be done in the field of electrolytes, and achieving full multivalent cation-anion dissociation is crucial for achieving high energy density. So. And now just briefly something about mechanism investigation. So we developed 2 tools which are quite useful and I think can find application also in other labs, and you might find it interesting. So first is Operando ATR infrared. So we wanted to measure infrared spectroscopy also during the cycling, so not to do it just ex situ, where you have issues with stability of the samples and also washing them and not being sure if they decompose in between. So we wanted a cell that will allow electrochemistry and at the same time also ATR infrared measurements. So we decided to put silicon wafer window inside into the pouch cell, and we got something like this. So we have ATR crystal, we put on the silicon wafer, and then on the other side we have cathode, and we basically probe from the back side. This is actually, it's quite nice, but also the issue of silicon wafer and the whole cell is the fact that you see also the stuff that you're not interested in. So basically the strongest signal that is here, it's silicon wafer, and then you have contributions of electrolyte, of your binder. But luckily for us, this carbonyl, it has these interesting peaks are here. So if we zoom in into this area, we can see quite nicely that this carbonyl peaks, it decreases during discharge, and it goes up in charge, and so on again. So again, but we said, okay, can we do this a bit better? And we decided to do differential subtraction. So basically taking the spectra at different points and subtracting them in between each other to basically to remove all the non-active parts. And here we can see that basically we can see now much better. So basically we see again this carbonyl going up and down during discharge. But then we also reveal this CO minus peak, which is here. So appearing in discharge and disappearing in charge. And additionally, we have here new bands appearing in between 1100 and 1000 here. So this is quite useful because then basically you can see basically all the infrared ER active changes during your cycling. To basically confirm this, we did also synthesis of model compounds. So we reduced anthraquinone to OH groups and then reacted them with lithium base to get this sample. And here we're clearly able to see this strong peak at 1370 connected with CO minus lithium. But one problematic thing that we saw is basically even when we stored this in the glove box for 2 weeks, it decomposed. So this means that really having ex situ samples, you have to be really careful to really measure them in the glove box, not expose them and measure them quickly. So because basically in a matter of few days or weeks, they can be completely different. We did also DFT calculation on trimer. To basically confirm this, we used trimer because this was the maximum size that we could use for DFT calculations. And then if we compare the different spectra of calculations and experimental different spectra, we can see that we have really good agreement. We can take this method even further, so not just taking start of the cycle and end of the cycles, but also subtracting cycle in between. And when we did this in this polyanthraquinone compound, it was quite interesting that we were able to identify some peaks which are reappearing in the middle of the cycle and then disappearing towards the end and then appearing in the middle here again. And this is actually what showed us. Basically, this does not go directly with 2 electron exchange here, but there is an intermediate radical anion in between here. And these peaks here, they belong to this radical anion. We could also do some observation of SEI formation on the cathode if we take the spectra at same state of charge but in different cycles. And if we analyze and take a look at the literature, we see that basically these infrared bands, they belong to TFSI anion. So basically also we have probably some TFSI decomposition, although we don't see it because Coulombic efficiency in these systems is quite high. So it's above 99%, and you would not expect it, but it's there. Of course, there are also limitations to this method. Like I said, we are probing from the backside, and the penetration depth is quite low. So basically, we just see few micrometers inside the cathode, and this can become a problem when reaction is not homogeneous along the thickness of the electrode. And this is the case when you have anthraquinone soluble organic compound. Is basically, you can see when you take a look at this spectra here, where you expect a lot of change in the plateau, you don't see anything, and you see something only towards the end. So this means that basically, because anthraquinone is soluble, you lose basically the connection between the electrochemical activity and the information that you get from the infrared spectra. So one option to go into the bulk, you can do X to X-ray Raman spectroscopy. So if you do KH of light elements, you know that basically if you do X-ray absorption, it is quite difficult because you probe only surface because the energies are in a range below 1 keV. And if you use hard X-ray probes, it allows you to probe into the bulk. But unfortunately, this then requires synchrotron light of high intensity because you have really small cross sections. But if you have synchrotron detectors, then you can also get quite good lateral resolution because you can actually pick the areas of the electrodes that interest you. So basically here we have 3 areas which are picked, and we can see area, this is like with the window before, this is our electrode, and this is then the backside. And you can see that basically this oxygen spectra is just present inside the electrode. And we did this on anthraquinone polymers because carbon-oxygen anthraquinone moiety has a specific resonance at 530 eV here. And you can see it's present in anthraquinone and also in both polymers, polyanthraquinone and polyanthraquinone sulfide. And when you do discharge and charge back, you can see that basically in discharge this decreases and then increases again. And you can actually quite nicely correlate this intensity with the electrochemical conversion that you get from the electrochemistry. We extended this also to the magnesium and aluminum. So first by preparing model compounds. So here is lithium salt, magnesium, and aluminum, and then doing the correlation. Although we have to say that this correlation is quite good between the electrochemistry and XRS in magnesium, but not as good in the aluminum. But this might be also connected with the fact that we did not synthesize the best model synthesis compound. So as a future outlook, towards the end, I would just like to say that we have new characterization tools, and we should really utilize them to enable better and new insights in the performance of the batteries. We think that preparation of model compounds and use of modeling is really important to confirm the mechanisms. We need to improve capacity utilization and long-term retention of organic cathodes. And if we really want to have high energy density, we have to move from anthraquinone, which is somehow model compound, to high energy compounds. And of course, like I said before, we should not store ion pairs. We have to store just multivalent ions without presence of salt and ions. At the end, I would like to just acknowledge the whole battery group, collaborations from NIC, Chalmers University, and Institut Charles Gerhard Montpellier, and Josef Stefan for XRS, and our funding from Honda and Slovenian Research Agency. With that, I would like to thank you for your attention, and we hope to see you on IBA in Bled in October.